Hello, my name is Miguel González, and I will be your host for today. Welcome and thank you for joining this MDPI webinar entitled Drones Technologies. This is the first webinar on our drone series, and if you wish to contribute to the topic of the webinar, please check the webinar's webpage and the special issues related. I would like to remind everyone that this webinar is being recorded and that we will post the recording soon at the webinar's webpage. Please note that you will have to be logged into SciForum to view the content. There will be 3 presentations today of 30 minutes each. The presentations will be followed by a Q&A session moderated by the chairs. So each presentation will be followed by a Q&A session. If you have any questions for our speakers, please, you could either type them in the Q&A box that is at the bottom of your screen, and remember to mention the name of the speaker to whom you address your question, or you could also raise your virtual hand and ask your question live. I will hand you the microphone. Today's webinar is chaired by Professor Diego González-Aguilera and Dr. Pablo Rodríguez-Gonzálvez. And I will introduce them briefly to you now. Professor Diego González-Aguilera received a bachelor's degree in surveying engineering and a master's degree in geodesy and cartography engineering from Salamanca University, Spain in 1999 and 2001. And then he was a research assistant at INRIA in Grenoble, France, in the Institute of Computer Vision and Robotics, where he also performed his PhD research on 3D reconstruction from a single view, graduating in 2005. He then founded the research group TIDO, Geotechnologies for the 3D Digitalization and Modeling of Complex Objects at the University of Salamanca. He is now full professor and head of the Geotechnologies Master and PhD program at the University of Salamanca and co-founder and CEO of the startup Image to Smart 3D. Our second chair today is Pablo Rodríguez-Gonzálvez, who is a surveyor, geodesist, and cartographer and has a PhD in photogrammetry, which he obtained in 2011. He worked 8 years at the University of Salamanca and then joined the University of León in 2017, where he currently is associate professor in the Department of Mining Technology, Topography and Structures. His main research lines include photogrammetry, 3D reconstruction, accuracy assessment, and radiometric and geometric calibration of the different geometric sensors. Finally, he is member of the National Management Committee of Cost Action for Harmonization of UAS Techniques for Agricultural and Natural Ecosystems Monitoring and co-editor-in-chief of the journal Drones. So that's it for me. Thank you very much for joining. Hope you will enjoy, and I'll hand now the floor to the chairs. Enjoy.
Thank you so much, Elena, for the introduction. Good morning, everybody, and welcome to this first webinar of Drones Journal. So I have to say a few words. The first thing that I would like to highlight is that we are celebrating our new impact factor. So the journal get a very important achievement, a very important milestones in terms of impact factor. So we get 5.5 impact factor in journal citation reports. And for sure that this is going to be a very important, let's say, point for the journal, and we hope the best for the next years in this journal. So my first words, I would like to give the thanks to the speaker, to the panelists. It's a pleasure to count with you. All of them are experts in the field of drones, in the different domains of drones. So thank you so much, Antidio, Luis Miguel, and Dimitrios for sharing with us your knowledge, your expertise, and for sure that this webinar is going to be successful with your presence. So let me now to share with you a few slides of the situation of drones, and in order to offer a clear overview of the drones journal. So as you can see, Drones is up to date the only international open access journal about the science, policy, and technology of drones and its applications. And Drones publishes reviews, regular research papers, communication, and short notes about the different drones value chains. So the aspect that Drones is going to cover, it's really wide. The roadmap opened by Drones journals covers all these vertical pillars that you can see in the slide, from the design, the development, and of course the applications. So today we are going to have a very good examples with our panelists, experts in the different domains. And I would like also to highlight the history of drones. So if we consider that the drones was launched in 2017, it's important to highlight that in only 3 years we get indexation in Scopus. And last year, for instance, we get our first CIT score 5.4 in Scopus. And this year, 2022, we get the impact factor for 5.5 in journal citation reports and a CIT score of 7.2 in Scopus. So as I was saying, it's a great achievement for Drones Journal, and we hope the best for the next months and the next years. So a brief overview of the different, let's say, rate of publication in drones. So it is clear the increasing and the improvement of the Drones Journal through the years. So we can see clearly the tendency, the positive tendency in terms of regular publication on the left, and in the case of special issues on the right. And also we have to have a look a little bit to the rejection rate, that it's also important when the number of submission increase, when we have to, let's say, guarantee the best quality of the papers and the best quality for the dissemination of drones technology. We have increased the rejection rate, and for sure this is is guaranteed thanks to the quality of the editorial board that the Drones Journal has built around all the editors that we are going to present later. So a brief overview of the author distribution considering different countries. And we can see here in the different graphics, the different countries that are taking part in the publications in Drones Journals, with a high percent of papers coming from USA, then Italy, China, Australia, Spain. It's they are statistics, but allow us to have an overview of the, let's say, the country's distribution in terms of publications. And also this is really important, and it's one of the main pillars of Drones Journal, is to have a good editorial board. So we can see on the right the different editorial board members coming from different countries. And especially this year, the last year, we decided to boost the editorial board, creating new sections. And thus with these sections, we created different section editor-in-chief, trying to push several, let's say, fields that we believe that can be especially potential in the field of drones. So in this case, we created 4 sections focused on design and development, drone communication, drones in ecology, and last, drones in agriculture and forestry. So these 4 sections are allowing us to boost the journals, to get more papers, to get more special issues, and thus to get a more impact factor. To end my presentation and introduction to the journal, let me show you this slide where we can see in a clear view that the median publication time is around 1 month. This is very good, especially for those scholars who need to publish their research in an efficient way. So Drones Journals guarantees an average publication times very, very attractive for those scholars, for those researchers that need to promote the research, need to give visibility to the papers and the research that they are doing at university, at the companies, or at the different environments. And now is the time to give the floor to our panelists. So let me first introduce our first panelist. It's a pleasure to have with us Antidio Viguria. He did his PhD at the University of Sevilla, and he is the CTO in avionics and systems at CATEC, CATEC is a research center focused on drones. He was a researcher from 2006 to 2008 at Georgia Institute of Technology in USA, granted by a Fulbright grant. He's author of more than 90 peer-reviewed publications in drones and aerial robotics. He has more than 14 years of experience in project coordinations, having participated as World Package Leader of CATEC, the Center of Drones and Research, in more than 20 European projects. He has also been project coordinator of more than 50 national projects, and he's also currently the project coordinator of piloting an Horizon 2020 project that involves 14 partners and has a budget around 9 million euros for 4 years. Finally, he is member of the board of Euro Robotics. The talk that Antidio is going to give us will review the last technology developments in CATEC that increments the autonomy level of drones, aerial drones. The increase of autonomy level in aerial drone is critical to increase the safety of the operations and also its efficiency, especially in multi-aerial drones operations, that is the swarm operations, in order to reduce the workload of the aerial drones operator. So these new developments include, for example, the use of onboard sensors to automatically navigate in GNSS denied environments, dynamic and real-time multi-aerial drones operations, and use of sensor for automatic detection and avoidance of obstacles and other aerial vehicles. So this is all from my side. So Antidio, please, the floor is yours. Thank you so much.
Thank you, Diego and Elena, MDPI, for inviting us for this seminar. So today we'll talk about advanced technology for highly autonomous UAS or drones. So basically, well, just first, very briefly, introduce you who we are. As Diego said, my name is Antidio Viguria. I am the CTO in avionics system of CATEC. CATEC actually is a research center managed by a non-profit foundation called FADA, and we are located in Seville. And we are focused on applied research, and we also have an office in Santiago at the northwest of Spain. As well, we manage a test center called Atlas, which is a flying test center that is open to anyone that would like to operate. Is in the mid-south of Spain, and it has two main characteristics. First, it has a segregated space, and secondly, a very good weather conditions. Actually, we have right now Lilium, the real taxi company, doing their flight tests at Atlas. So you can have more information in the web page. So, highly autonomous UAS. So the market is demanding more and more autonomous drones or UAS. Why this is happening? Because they can increase the efficiency of the mission. They can do it in less time, or they can do it more with better quality of the data. Secondly, and this is very important, we really believe that the operation could be safer, much safer than with the poor teleoperation. And even the integration into the space could be even safer. And of course, when you increase the autonomy level of the drone, you will require less training and require skills for the pilots. So the pilot will be easier to train new pilots and will be easier to escalate the business of drones. So that's why the market is more and more asking for a highly autonomous drone. Also, it's important to point out that the recent European drone regulation already allows the operation of fully autonomous operations without a pilot at all under the specific category. So I don't know if you're aware that the European regulation considers three main categories: open, specific, and certified. And in the specific one, which is in the middle, which is a gray area that allows flying in cities, flying large distances, flying close to infrastructure, flying large drones in sparsely populated areas. So in this specific category, it is allowed to have the operation under the current regulation of fully autonomous drone. And this is a very good step in terms of having some framework, legal framework that allow this type of operations. And in order to accomplish this higher level of autonomy, we need to develop new technologies. We need to develop GNSS, free navigation, landing in complex spaces, detect and avoid, autonomous tracking, or multi-UAV. And today I'm going to talk briefly about some of these technologies that we have been developing the last 10 years at CATEC, with some examples to illustrate a little bit. So, first of all, we have the GNSS free navigation. So for GNSS free navigation, when this is important, this is interesting, for example, when you are performing a inspection close to infrastructure. For example, in this example that you can see here, what you can see the UAV flying very below a bridge, so you don't have a real coverage of the GNSS. So in this case, we are developing a solution based on SLAM. SLAM is a technique that comes from the robotic that allows to have at the same time, as you can see in the video, a 3D map of the environment and a localization of the robot in that map, within the map. So what is performed, it scans the environment with the LiDAR. The LiDAR performs, you have a 3D point cloud, and then you scan it again a few moments later. And then you see how this matches, and then you can estimate the relative position. So we have performed different experiments, as you can see here, and we can see that we can actually localize the UAV very precisely, less than 20 centimeters of error in this kind of environment without any kind of GNSS solution at all. So as you can see here in this video, the UAV is, with this navigation solution, is able to perform waypoint navigation. So this is very important because instead of being in this complex environment, instead of being able to teleoperate it, you can just plan a waypoint navigation. And this is also very important for inspection applications, and this is part of the piloting project that we are leading, because you can have repeatability. And this is also something that they look a lot with the drones, to have repeatability. So you perform exactly the same trajectory one time, another time, another time. And this is only possible when you are able to have some level of automation in the drone. And for that, when you don't have GPS, you need this kind of techniques where you are able to perform GNSS free navigation. So this is the solution that we are developing. This is interesting that also an important problem with that is the localization framework, okay? So this SLAM technique is a relative localization system. So it tells you how far you have been moving from an initial point. However, in order to inspect, for example, inspection or to navigate in a city, you need to be located with respect to the framework, specific geolocalization framework. So in that case, what we are doing is that we have a previous 3D map of the bridge in that case, as you can see on the video on the right, and I will put it from the beginning. At the beginning, you have at the right the 3D map coming from the UAV, from the LiDAR. And then you have the original 3D map that is located in the geographical framework of the bridge. And then what we do is that we perform automatic alignment of these two maps in order to have the drone in the global reference system for all the inspection. And this is very interesting because in that sense, with this transformation, we are able to first, it's much easier to plan the trajectory of the drone because you can plan directly from the 3D map using the global reference system, and also the information gathered by the UAV, for example, the images, are automatically your reference to this global reference system for all kinds of inspection. So we have developed this procedure and these techniques that allows to have this automatic alignment in order to facilitate the operation of the UAV in, for example, in the inspection of infrastructures. Okay. Also, it's interesting that we also are performing GNSS free navigation application for example, for the inspection of sewers. This is a very interesting project that, first of all, we develop a navigation system that allows us to navigate inside sewer, okay, that you don't have GNSS at all. And also, as you can see here, the objective, and this is in a real sewer, the objective was also to be able to operate without having anybody inside. So we managed this tool, a specific tool, in order to be able to later on, once the flight is finished, that we can recover the UAV, you know. So you can see here the video and the coming, and then you can see how the UAV is captured. Okay, so we are also applying these techniques to the inspection, for example, of sewers with GNSS navigation. Also, all this technique can be used as well. This technique can be used as well in urban environments. In urban environment, for example, we have this DeLorean project where we are developing navigation solutions for this urban environment, especially for landing and taking off when you are in these urban canyons, when, okay, you have some GNSS coverage, but maybe it's not so good. So we are evaluating how we can complement the solution from the GNSS with a solution with onboard sensors. So in that sense, with having that in mind, with that sense, we can actually be able to enhance the GNSS solution and maintain a good resolution during the whole flight. So in this flight, you can see we have been flying in Benidorm in a very realistic, it's a city, but with a very nice sky view. And we have performed a number of flights in order to gather data and see how we can use this LiDAR information in order to complement the GNSS navigation solution in these urban environments as well. Another interesting point is autonomous landing in complex spaces. So this is a vehicle that we are developing to inspect pipes in the refinery. So this is an interesting concept. Here we have an aerial vehicle that has some sensor that allows to detect obstacles. So it's not only it's able to detect obstacles and navigate in cluttered environment, as you can see here, and once it is on top of a pipe, we automatically detect the pipe and we're able to align with the pipe, and later on we are able to perform a landing, automatic landing. This could be very difficult to do it manually, you know, and especially when you are working ahead, because the idea here is that we are working ahead. And once the UAV is landed, we are able then to inspect them with a special crawler that we are transported. So this is very, very interesting concept that, for example, here, this was in a testbed, but we are going to perform experiments in a real refinery. So here we can see how the robot has some certain autonomy capabilities that allows to detect obstacles, to detect, even if it is teleoperated, it has certain level of autonomy and allows to be able to navigate, you know, through complex spaces and perform complex operations such as landing. Also, we are working on detect and avoid. This is an interesting project. It was a project where we had also a LiDAR on board, and we were able to detect, for example, a building and change automatically the height of the flight so it can avoid the building. Okay. The interesting thing here of this project, even though you cannot see in the video, is that all the processing was performed on an external server. So we were connected to a 5G base station with a edge computing server. So the server was actually close to the base station, and we were able in real time to send the whole point cloud to the server, compute it in the server, and then send some commands back to the UAV. Okay, in order to in real time, and everything in real time, to change the altitude of the UAV. And this could open a lot of interesting options in the future, in the sense that you could decrease the payload or decrease the computer capacity that you need on board, and perform even critical tasks, critical functionalities using the computing capabilities that offer 5G. So this combination of 5G and drones, we think has a lot of potential and can be very useful, especially in urban environment. You're going to have very good coverage in order to have a computational capacity, even for critical application outside, in the server, not on board. But since the communication is very good and in real time, it has a lot of bandwidth, it can even consider that some of the software modules that has to run in real time that usually are on the drone, they are on the server. For example, as here that we are doing this detect and avoid. Also, another thing that we are doing this is what we call onboard autonomy. So being able to have enough sensors and also computational capacity and reasoning on board. So you're able to perform complex tasks. For example, here, this was a proof of concept. So we have a UAV that you have these green balloons around. You don't know where they are. So the UAV with the sensor has to map the environment, has to locate the balloons, has to get approach to them. And without any intervention, fully autonomous of the pilot, it has to get close and explode them. Okay, that was a first task and was, I would say, quite easy or easy. The second task is much more difficult, is the one that you can see here, that there is, I don't know if you can see, there's here another drone with a yellow ball. And here you can see how the one drone is able to automatically, without any intervention of the pilot, to detect the ball, track it, get close to it, and then capture it. Okay, so this is everything done automatically. And this is something that involves perception, onboard perception. We had two cameras, one with long range capability, another one was a 3D camera for the last part of the tracking. And then also you have reasoning. You have to reason, you have to perform complex algorithms for guidance, for tracking on board. And everything in this case was performed on board the vehicle. And it was also performed part of the assistant project, the project that we, also European project that we are developing. Then, of course, we have performed also some interesting solutions in for logistics. Okay, we also have this onboard autonomy. So here, in this case, we actually perform a pilot in a aeronautical factory. The concept was that you have an operator that requires a certain component, a small component at a moment, and instead that the operator is moving inside the factory to a certain position, then to grab it, the UAV will bring to him. So he doesn't have to waste time, moving around the factory to get this component. So now you can see here, so it was a fully autonomous UAV that is able to transport these small components, is flying the real factory with people around, and it's able to compute the localization with the onboard sensors. He's able to navigate without GNSS, is able to detect obstacles, is able to plan the trajectory, and is able to localize, to able to have with such precision that it was 1 by 1 meter device, the one that we use for the delivery, and it worked quite well. So you can see here how the operator at the end, he gets what he was asking for. Okay, and everything was performed in automatic way with no intervention of the pilot at all. And this kind of technology is the thing that we are developing, and we think that could help, to increase the efficiencies of some services. Also, for example, here there is an application on surveillance, where here you can have a drone that is able to automatically survey an area, and when it finds a person or an objective, it can automatically change its mission without any intervention of the human and start tracking it. So it's doing around, and when it takes a person, it's able to follow it and move it, and not only with the gimbal, but also with the movement of the UAV. And then once it loses the person, for example, here that is hiding, it will change to another mode of operation that it has to go around and try to recover the track of the objective. So this kind of decision making, this kind of onboard autonomy, even more complex than these ones for different applications, it will allow to have UAVs that can respond faster, that can respond to uncertainty in the environment, and can also be used to work, can be used to increase the efficiency of these tasks as well. Okay, so here you will see that it finds again the person and is able to track it again. And all this embedded artificial intelligence, it's something that we work a lot at CATEC. So let's go now to multi-UAV. Multi-UAV is very interesting because it allows to solve some problems, easily. For example, here we have an area, and it was a proof of concept, and we have an area that we need to ensure the coverage with the radio communication system. So the color circles of the communication coverage that the drone is supposed to have, with the onboard communication system. And what we can see here is that the drone, of course, they don't have a battery for being persistent all the time. So you have an extra drone that is able to exchange it with the other ones the battery is decreasing. So in this way, you can see here how a team of drones can perform a task and that is provide a coverage on a certain area, and then use this extra drone in order to exchange it to maintain the coverage, even when you are having some problem, for example, with the battery, that you have to recharge or whatever. So this kind of mission are very, very interesting as well. Here you can see, for example, we are also working on trajectory planning. You can see a number of vehicles that they have to go from one side to the other of this indoor test bed, and they are exchanging the information in real time, and then they are replanning the different trajectories, so they don't collide to the obstacles and they don't collide to each other. So originally they have a collision point in the middle, so they change the trajectory in real time, just broadcasting the information and the intention that they have in order to be able to don't collide with the obstacles. In this case, the obstacle was a previous map, and with themselves. So this multi-UV trajectory is also some techniques that we are also applying for example, for tactical deconfliction in US space environments as well. Then also, it could be very interesting to have swarming flight formation. So operator, for example, can handle a complete fleet just moving the leader. See here, you can see how there was this triangle formation, and you can see also when you have obstacles, how the formation automatically changes its topology in order to be able to adapt to the environment. So this was a dynamic distributed algorithms that was running in each of the UAV, and were able to communicate with each other, and were able to change the topology in real time of the formation. So they can go through places that originally the formation, and this is done completely automatic. So this is very interesting because the operator doesn't have to think about how to change the formation to go. It just goes through, and then the formation is the one that automatically changes its topology. Okay. Yeah. Here, this is also some more multi-UAV application that we are developing, for example, for such operations. So we have what we have here. We have 3 autonomous UAS that they will perform the operation in outdoor environment, and they are able to automatically cover a large area and divide the task among the different ones. Okay, so you can see here below, so you have 3 different ones that they go to the 3 different locations, and they can cover the area in a different, let's put it again. So they cover the area automatically between the 3 of them. An interesting thing is that once one of each detect an objective, is able to also ask for the other to perform a cooperative track, so they can increase the precision. So as you can see here now, in the back part. The red one will detect objective, and the other two will come closer, okay, and they will be able to increase the precision of the localization and robustness while tracking, because you have the 3 points of view, you know. And this is I will now illustrate it with a video, how this is performed and also illustrated. So here you can see how the three robots, they can track a single objective in a cooperative way, you know. So they were able to track it and also to maintain the formation in such a way that you have different point of views, and you can also be able to track them. Okay. So coming to an end, I would say, so more and more autonomous and interconnected UAS drones are demanded. We have been talking about onboard autonomy that allows safer operations, detect and avoid, tactical deconfliction. These kind of things are very interesting in the next for the future applications. More advanced flying modes, where you require less required skills for the pilots and the operators, and autonomous planning of the missions, where you can have more efficient and more competitive applications. So, as I said at the beginning, the current European regulation allows this highly autonomous operation, and of course, we have been working in the last 14 years on this technology. I just show some of these, I would say, applications, missions, very briefly. It's true that very briefly, but it's something that we have done in the last 14 years, and I hope that it was interesting for all of you. I think we are just in time, so thank you very much for your attention. I hope it was interesting.
Thank you so much, Antidio. It was incredible, the talk, for sure. I had reference about your progress and your achievements in the institute, but it's incredible. You are covering a lot of topic trending in drones, from SLAM, automatic alignment, robotic operations, logistics, surveillance, and even this swarm operation. So it is time for the questions. I don't know if someone from the participants or even the panelists has a questions. There is one in the chat. No, this is not the. Okay, by the way, I am going to ask you several questions related with some of the different applications that you show us. The first one that it's really interesting for us is related with let's say the SLAM operation, that the approach that you are applying in the bridge, for instance. I was wondering, when you are doing the alignment between the different, let's say, campaigns to analyze and to assess the health of the bridge, I was wondering about the detectors and descriptors that you are applying to get success in the alignment of the different models. Could you provide some more technical info about that?
Well, the alignment is to have the same reference system, you know, global reference system. So actually try to minimize the error between the current map that you are seeing as a previous map, okay, that we have gathered. You know, so usually what we do when we do inspection for infrastructure, we first go with, for example, total station. We have a 3D map, your reference, with a certain global reference system. And then what we're doing with the UAV, you don't have to, you can start the flight whatever you want. Then you start fly and you gather a first 3D map. And then what you do is you align automatically this 3D map with the previous one. And then now the UAV is in the same reference system. So then you can perform exactly the same flight pan and waypoint navigation that you did, for example, 1 year ago. You know, because the bridge is in the same place and you are referring to the exactly same global reference system.
But imagine that you need to, let's say, to get more accuracy, because the GPS, as far we know, in real time is going to provide maybe centimeter of accuracy, right? So if you need to align the data set with more accuracy, you are applying a specific approach to, let's say, to fuse all the data set.
For that you can do is that sometimes what we have performed is to use some basically some control points at the end. You need some control points at the end on the infrastructure. So if you get images and then you can recreate the model taken from the images and you have some control point, this will allow to decrease a lot the precision of the system. But without that, it's difficult to go less than what we talk about 10 centimeters, something like that. It's more or less real.
Okay, and before coming to the chat, that we have one question related again with the SLAM. We are dealing with this approach in different applications, but the main drawback that we found is that in several applications, like galleries, for instance, you show several galleries where the texture is really homogeneous. And in this case, the SLAM didn't work very well, because the texture is not very, let's say, favorable to match. Okay, how did you solve this approach?
For the SQL, actually, we were not using SLAM. What we did was more in that point. What the end user wanted is just to be able to maintain the distance from the different walls. So at the end, what we did is that actually we maintain at the center, and then was some guided algorithms just to from input from the user to accelerate or decelerate. So actually, you were not actually knowing exactly where you were, where you were, just to navigate in this special environment. It's true that with these tunnels or things like that, the SLAM sometimes it's more difficult, but it's true that sometimes that you can do is try to also to, as I said before, try to detect some kind of features. For example, we have performed some things, some large tunnels, and in the large tunnel you can see you have lights, you have some signals and things like that, and this could facilitate a little bit,
Okay, and a last question from my side. When you are applying the recognition from different drones, or even from a unique drone, you are, let's say, solving the boundary of the object in movement. But I was wondering if you are also computing the pose, I mean the position and the orientation of the object that is moving. In this case, the person that was moving through the vineyards.
No, in that sense, in that case, no. We are more focusing on detecting and positioning the person, but not the pose. I guess that for the pose, probably you need to also to fly closer and also get some kind of also model of the human body, and also to understand the what are the arms, what is the main body, the legs, and then maybe you can start estimating some pose. But right now we're focusing, I would say, on the location of the person, of the vehicle, or whatever.
Yeah, I mean with the pose, I don't mean the let's say the position of the arms and the legs. I mean the coordinates, the 6 unknowns related with the spatial position, X, Y, and Z, and the angular position. Okay.
No, we are more focused on the X, Y, and Z.
Okay.
In that sense. And of course, well, probably what is, I mean, in some way you could also estimate in some way what is the heading, I would say, with respect to the north. But then for the roll and pitch, I don't know if for us it was not a valuable information.
Okay, thanks a lot for your answer and your presentation again, Antidio. We have one question in the chat. It is saying, excellent presentation. Can you focus the use of drones for spraying purpose in agriculture?
Well, yes, of course, this is an interesting application. And there are some products on the market for spraying. I guess that here the technological challenge will be maybe when you have different slopes and very terrain with different slopes, and also be able probably to automatically maintain the same height, you know, even with complex geography with agriculture. So these are interesting problems, I would say, but especially, I mean, particularly us, we have not worked in those yet.
Okay. Okay, we have time for one question, no more. Any question from the panelists or even Pablo? Do you have any questions?
There is one question in the chat, actually.
Okay. But Elena, do you mean the question
From David Kwaf Kamchat? Do you see it just before
What
me?
is a best drone for above ground storage tank internal inspection? Okay. Okay, so for, I would say that, I mean, I don't know if what he's referring exactly. For tanks, I know there could be two types of inspection. One is wall thickness inspection that you need to maintain contact, for example, with ultrasonic. Another one, it could be a visual inspection. For the contact inspection, there are different products already in the market. For example, there's a company that has a technology developed by us called VES Robotics, VES Robotics, and this has a technology that can be used for that. And there are others, for example, there's another one called Voliro that also has a technology that allows this contact inspection. For them, I would say for internal track visual inspection, well, you will need this kind of automatic positioning system. And also it depends how, I mean, if you wanted to make it more autonomous, if you wanted just to have it, I would say visual inspection teleoperated, or there are different kind of drones already on the market, no? So I think if you have any question, you can maybe send me an email and I can point you to some of those.
Okay, thank you, Antidio, for the answer. Is there any question, Pablo? No?
Hello.
Hello, we can hear you, yes.
Yeah. So I want to ask one question on how we can use the drones for spraying of the herbicides or pesticides in agriculture. Because nowadays, as our government of India has given a subsidy for these drones, and we have to calibrate the use of drones in agriculture. So any experiment or any studies is there with you? So can you please highlight on this aspect?
And I think that I understood the question is what is the use of drones for agriculture, no? Or something like that. So there are different, I mean, there are some applications used for remote sensing, I would say. So you can capture images and you can get some indices in order to detect water stress, or also if there is some disease on the crop itself or something like that. This is a very well-known application, and usually you use multispectral cameras. Then you have the spray ones that was commented before. And then I would say it's any kind of visual or remote sensing application that instead of using satellites, you could use drones. So the drones has the benefit that even if it's cloudy, can get images, and you can get the data when you need it. No, you don't have to wait the satellite to be on the spot. I hope you.
No, for operations like spraying of nutrients or spraying of herbicides. If suppose we have to apply the herbicides to the crop before emergence, so at that time, what could be the height of this drone, or what will be the proportion of the speed? Because all the herbicide that should be sprayed over the surface of the soil in equal way. So for that, if you have conducted any experiments or any data is there, so can you please highlight on this aspect?
I didn't get it, Diego. Maybe you
I don't know if you are asking about the height of the system I mean the price.
No, not price, height. How, if suppose from the soil surface, how much drone should be flied so that there is a equal distribution of the any herbicide or any insecticide or pesticide for controlling the weeds as well as the disease and pests.
If I, Diego, sorry, yes. If I understood correctly, the question is, do you know, Antidio, anything about how to spray, provided you already know the situation with the crops? So some parts may need some more spraying and some other parts less spraying. How can a UAV be used on spraying differently in different areas and different amount of?
Of course, I understand that you have. You have the drone knows where it is. It has some GPS, it has some localization system. So you have a task map. I would say that you know exactly where you have to go and to spray certain amount. Then it's the only factor is to have a flexible or versatile system that allows you to spray at different levels at a different position, you know. So it's more a development of having automatic or a machine that allows you to spray differently, you know, at different rates and depending on the position. And this can be easily automatized. Yes.
Yeah, thank you,
Okay.
Dimitrios, for the clarification. To give more input in the question, that it is really interesting. It is clear that to provide a service with these capabilities, the previous step is mandatory and requires to have a perfect knowledge of the state of the crop. And to this end, as Antidio was saying, I think that the extraction of indices and the different maps, risk maps related with the crops and with the health of the crops allow us to, let's say, to have a clear overview of the health of the crop, and that to regulate the spray of the fertilizer or of the whatever substance that we can put on the crop. So I think that it is something that could be automated, but it's interesting. Yeah. Another problem that we have to face several years ago was to assess that the company that was spraying the fertilizers did in a wrong way. I mean, put the wrong amount of fertilizer in the crops, and as a result, the crops was completely damaged. So we have to assess that in the end, this damage that the owner said that was happening in the crop was true, was real, and we have to check the quality of the fertilizer sprayed along the crops. Okay, thank you, Professor Wagner. Okay, I don't know if there is any more questions. It is said, thank you for the presentation, Antidio. Do you believe swarms of drones, an autonomous system in border management and control, could be a solution that could be implemented in near future?
Yeah, I think so. I think it's we have to clarify what is near future, but I think it's a potential application for sure, you know, to have a team of drones in order to appropriately have a border management and things like that. Also in the defense world, they are also looking a lot into swarming in order to see how they can collaborate with fighters and how they can also collaborate by themselves. So I think actually this is a potential, a very target application, and we will start, I think, seeing things in the next, I would say, 3-5 years, you know, about that.
Okay, thank you, Antidio, so much. There is no time for more questions. We have to move to the next speakers, to the next panelists, because the time is limited and the audience also is limited. So thank you a lot, Antidio, for the presentation.
Thank you to all you. Thank you
for the answer and the question and the debate. So it was great. So let me introduce to the next panelist. His name is Luis Miguel González. He is a postural researcher at the University of Vigo, Spain. His PhD and current research is focused on the development of aerial drones for infrastructure inspection tasks, specifically in the development of payloads for contact inspection tasks in large infrastructure, such as bridges or dams, as well as in the development of path planning algorithms for drones navigations in the neighborhood of structures. Also, he is founder of Unmanned Galicia, a spin-off of the University of Vigo, focused on the development of specific drones, payloads, and methods for different kinds of inspections. He is now collaborating with the Institute for Sustainability and Innovation in Structural Engineering at the University of Minho, Portugal, developing new methods for infrastructure inspections using aerial drones. The talk that Luis Miguel is going to give is about the development of specific payloads for aerial drones and inspection methodologies for large infrastructure, especially focused on performing non-destructive techniques, contact inspections with aerial drones. So please, Luis Miguel, the floor is yours, and thanks a lot.
Okay, so good morning, everyone. Thank you so much for your introduction. First, I would like to congratulate the journal and the editors for the impact factor you have achieved, and also for organizing this webinar, which I found very interesting. Also, I would like to thank Dr. Diego Aguilera and Dr. Pablo Rodríguez for inviting me to this webinar. For me, it's an honor to participate in this webinar. And my name is Miguel González. I am a postdoctoral researcher from University of Vigo, and my presentation is focused on the development of UAV payloads to carry out contact inspection tasks in large infrastructures. So this is the structure of the presentation. I will start with an introduction, highlighting the motivation of the work with a small analysis of the state of the art. Then I'm going to introduce the 3 versions of the UAV contact inspection system we have developed, and then I'm going to talk about the future developments we are planning to do. To end the presentation, I will introduce the conclusions. So in the last years, the use of UAVs or drones has increased rapidly for both professional and recreative use. And in the professional sector, the main advantage of these vehicles is that they are a low-cost system, able to reach hard accessible areas, and also they are versatile systems that can be used for many different applications, as we have seen in the presentation of Dr. Antidio. These vehicles are already used in many different fields, such as civil engineering inspections, agroforestry applications, military applications, among others. And even with all these advantages, the main drawback of the UAVs is the actual battery capacity that limits its operations. So in the civil infrastructure field, there are some similar structures, as can be bridges, dams, or wind farms, where a series of inspections have to be performed during their life cycle to ensure its structural health. Some of these inspections are already carried out by UAV using non-contact sensors, such as different kind of camera, LiDAR sensors, or radar sensors. But some other inspections use sensors that have to be in contact with the structure, such as accelerometers or ultrasonic sensors. And currently, these operations are carried out by operators working at height using cranes or scaffoldings. And these operations are slow and costly. So the next logical step is to develop UAV systems able to perform this contact inspection task. And this is where my research is focused on the development of these contact inspection systems. So the UAV physical interaction with the environment is a field where several researchers have been working on. Initially, the developments were focused on installing a robotic arm to grab objects, which is not directly applicable to the contact inspection task. But in the last years, some authors have been working on develop these contact inspection solution systems, and different approaches have been proposed, such as the system based on a vertical gas to maintain the contact, or systems able to clean walls, as this one. But the most common solution is the installation of a manipulator in the UAV with systems as simple as this one, which is composed by one linear passive joint, and other more complex systems as this one, with a manipulator with 6 degrees of freedom, where all the joints are active. In fact, this work, I think, is or have been done in the CATEC. So it's work, Dr. Antidio. So it's a pleasure to share or to participate in the same webinar of this outstanding research. So probably the most important component of these systems is the control algorithm, where the most common control algorithm used on these vehicles is the PID algorithm, but other solutions have been implemented, such as Cartesian impedance algorithms or control algorithms based on the dynamic model of the vehicle. Regarding the positioning system used in these vehicles, most of these vehicles use GNSS data to positioning, but it is not reliable for contact inspection tasks since the neighborhood of the structure is a GNSS denied area. There are two main alternatives: positioning systems installed on board the UAV and positioning systems installed off board the UAV. In the first group, the most used systems are based on SLAM algorithms, which can be used with both LiDAR sensors or cameras. And in the second group, two systems are the most used, one based on ultrasonic beacons, and the other is vision-based systems that use cameras. For contact inspections, the positioning systems of this second group cannot be used since several cameras or beacons have to be installed in the area where the vehicle is going to navigate. So for contact inspection systems, the positioning system has to be on board the UAV. So now let's start explaining the systems we have developed. During my PhD, 3 different versions of the system were developed, each one improving the results obtained by the previous version. And we colloquially call this system Contact 1. So this is the first version we have developed, which was published in Sensors Journal in collaboration with researchers from University of Porto in Portugal. And the payload is basically composed of 3 main components that are the sensor support, the contact support, and the positioning system. In this version, the contact support was developed or was designed to be flexible in order to absorb the vibrations of the UAV during the contact inspection. All the versions developed use the same positioning system that basically consists on 2 parallel distance sensors installed in each side of the UAV and orientate forward the vehicle. With these 2 distances, the systems calculate both the distance between the UAV and the structure and the angle they form. In this case, the system used 2 LiDAR light sensors, which are time of flight sensor with a range from 5 centimeters to 40 meters. And once the payload was installed on the UAV, the positioning system was calibrated. The payload has its own processing unit, and it was designed or it was developed to be completely independent of the flight controller of the UAV. In this way, it can be installed in different platforms or configurations of UAVs. The control systems calculates the distance and the angle between the UAV and the structures where the inspection is going to be performed, and then calculates the yaw and pitch signals for the flight controller to perform the approaching and the contact with the structure. In this case, 3 operational modes were defined. In the first operational mode, in the manual mode, the vehicle is completely controlled by the operator. In the angular mode, the payload actuates over the yaw signal to control the angle formed between the UAV and the structure. And in the contact mode, the payload controls both the yaw and pitch signal in order to perform the approaching movement, ending on a stable contact with the structure. In the angular mode and contact mode, PID algorithms were used to control the signals, and also in the contact mode, an hybrid automaton system was implemented where each state of this hybrid automaton represents a possible operational state of the drone during the contact inspection, and each one implements a different control algorithm or different control variables. This system was tested on an indoor laboratory, obtaining good results. And analyzing these graphics, we can see that the approach movement is very fast, and the vehicle bounce in the first contact. The yaw control can be improved. And as we can see, during the stable contact, the system is not able to be completely fixed to the structure. This is due to the flexibility of the contact support, and taking all this into account, we developed the second version of the payload, which was published in Automation in Construction journal, and several improvements were introduced in this version, from the modification of the contact support, making it more rigid, to the control algorithms. A new contact support was designed, wider than the previous one and more rigid, and also a new sensor support was designed with a linear passive joint to mitigate the impact in the first contact with the structure. Another distance sensors was added to the positional system. So as we can see in this graphic, the LiDAR lead sensor has a range around 90 centimeters, where it is not able to take reliable measurements. So this new sensor solves this problem, complementing the LiDAR lead. And a stability system was implemented to select the sensor used in each moment. Regarding the control system, just small changes were done. In the hybrid and automaton system, a new state was set, and the control variables were tuned to make a slower approach to the structure. The payload was integrated in 2 different UAVs, and comparing the obtained results with the previous version, we can see that we have reduced the bounce with a slower approaching speed, and also with the new contact support, the system is able to be completely fixed to the structure during the inspection. The system was tested in both indoor and outdoor environments, obtaining good results, and to maintain the contact, the UAV have to push the structure using the pitch signal. And this is not very efficient, since just the horizontal component of this force is used to maintain the contact. So taking this into account, we developed a new version, or the third version of this payload. But in this case, it is an active payload that contains 2 motors in the back of the systems to make this approaching, and also to maintain the contact. The structure of the payload is almost the same, adding 2 motors in the back of the payload, and the control algorithm are almost the same. Just the contact mode was modified. Now the payload does not actuate over the pitch signal to make this approaching movement and maintain the contact, and now it actuates over the payload motors to perform the approaching movement. The system was tested in an outdoor environment, obtaining good results and increasing the flight capacity of the UAV. So this we have developed these 3 versions in the last years, and now we are working on a new strategy for this contact inspection. We have changed the strategy in this case, instead of maintaining a continuous contact between the UAV and the structure, the idea now is to go with the UAV to the structure, fix the payload to the structure, and when the inspection is finished, recover that payload. We designed this new strategy in collaboration. We are working in collaboration with University of Minho, and the idea is to use accelerometers in these contact inspections. The main problem of the previous versions is that when the UAV is maintaining the contact with the structure, the vibrations of the motors of the UAV affects to the measurements of the sensor. That vibrations affects to the measurements of the accelerometer. So in this new development, the idea is to install the sensors in this box and attach the box to the structure. We have done this development in a company that we have found, which is called MANE Galicia, that is a spin-off of University of Vigo. And as you can see, it is basically a box where the customer can introduce any sensor, of course, with some size and weight limitations. And the idea, as I mentioned before, is to fix the box to the structure without maintaining continuous contact between the UAV and the structure. This is the first functional version of the system, and we are working on improving it. Of course, this is a development we have done in the company, so it is not published in a paper. So to conclude, UAV systems for contact inspections have a great advantage over current NDT inspections methods. The development of these systems is a topic where several researchers and institutions are working on, and in the next years, commercial solutions are expected to appear. So this is the end of my presentation, and now I'm at your disposal to solve all your doubts. So thank you for your attention.
Thank you so much, Luis Miguel. It was incredible presentation with the verticalization of these techniques in contact inspection system. So for sure that you are going to get success with your spin-off. So I hope that in the next year we can see these, let's say, services in the north of Spain, but especially in all Spain with these techniques. So I was wondering, seeing your presentation, that sometimes in our group we are dealing with the inspection of materials. And for this inspection of materials, trying to assess the deformations, sometimes the techniques that we are applying are non-destructive techniques, and these techniques are based on digital image correlation. Digital image correlation allows us to get very high accuracy and reliability in assessing deformation of materials with, let's say, with a very stable framework. So if we apply this digital correlation in situations where we control the cameras, we control the stability, the setup of the sensors and so on, the results are really good. But when we try to face this problem in some remote places like bridge or like let's say aeolic parks, where we have to assess the quality and the pathologies of this type of elements, I was wondering if you consider to include in your system with the different arms the possibility to perform digital image correlation in 2D or 3D using an stereoscopic arm.
Yeah, in fact, in this postdoctoral fellowship that I'm doing in University of Minho, they are experts in infrastructure inspections, and one of the projects that they proposed to me is to develop a similar system of the three versions, the three first versions, where the UAV is in continuous contact with the UAV, with the structure, and changing the payload, the sensor, to 2 cameras in order to detect small cracks in bridge. Of course, this is a work we are doing right now, so we have no results to show right now, but I think this kind of systems can be interesting, because the second and the third version of our payload is rigid, is very rigid. So you can maintain or you can fix the cameras to the structure, and in this way, I think we will be able to measure that small cracks which have millimeters. So I think this system can be used for this kind of inspections. And also in the new version of the payload, you can the idea is to install also cameras. So you can install a camera in the bridge and make all the inspections you want, and then recover the sensor.
Mm-hmm. Okay, interesting. So coming back to the spin-off experience, are you focused only on, let's say, infrastructure related with bridge, or do you consider to open this approach to other type of infrastructures?
Well, we offer many different services with UAVs, but in the research area, we are focused on inspection of bridge inspections with this payload. The main problem is that we are a really small company, so we cannot apply this technology for many different fields. So we are focused on bridge inspections.
Okay, because we are involved now in a project that allows us to assess the health of bridge, but let's say in a course level, trying to use satellite images using DINSAR and radar to let's say to detect movements in the terrain. In fact, several days ago, we can see in the news in Spain that a bridge collapsed in the motorway. And for sure that this technique can be complemented with your approach, because maybe our approach allow us to filter those infrastructures that are suffering some movements and subsidence movement in the terrain, and then we can apply your fine approach to assess the health of the bridge, right?
Yeah, yes, for sure. We developed this system to try to avoid this kind of disaster. So yes, that's our goal, to apply this technology to bridge to avoid this kind of situations.
Okay, thanks a lot again for your presentation and answers. Is there any questions?
Yes, Diego, we have questions from David Wanchat. He said, surface preparation of contact inspection using drone is one factor for success. How to deal with, for example, ultrasonic thickness testing? A stable control for Prof holding is required and no raw surface. Luis Miguel.
Well, yes, we distinguish between two main contact surface. In one hand, we have the metal structures, where we use, well, I don't know how to say in English, imam. Well, we use the magnetic properties to attach the payload to the structure. And in the other hand, we have a concrete bridge, where we use special glues to attach the payload to the structure. In the case of ultrasonic thickness, I can show you again the place where we test the system. We use the system in this wall that have a metal glue sheet in the exterior of the wall. And of course, we are not focused on the development of the contact sensor. We are focused on the development of the payload to perform this contact sensor, this contact inspection. So in this case, the sensor we use that is in the publications, it's a Kitex sensor, and it works in this case. But we are not focused on the development of the sensor. We are focused on the development of the payload to perform the contact. So I don't know if that.
Thank you so much for the clarification. Is there any more comments, questions, discussions? You have a little bit, 1 minute or more or less. We have some in the chat. Thank you for the very interesting presentation. This is said by Dr. Hamad from UPM in Malaysia. The first point is some of the drone flight endurance is limited by the battery power. Is there any new technology developed to provide better flight time as opposed to current one? This is the first question.
Well, in our case, what we did is to develop that third version that have the motors in the back. And in this way, we develop an efficient, more efficient system. But we don't work in the development of new technologies to improve the flight endurance of the UAVs. So I cannot help you in this field.
Okay, and the second one is, can the system developed by Dr. Luis be used also to conduct soil assessment horizontal?
Well, I don't know what means exactly soil assessment.
Yeah, maybe, I don't know if coming from Malaysia, I don't know if it is focused on agriculture again. So sometimes for the soil assessment, this type of techniques can allow us to, let's say, to have a clear overview of the nutrients that can be within the soil. So if we use ultrasounds and this type of techniques, maybe a relationship can be found to see how is the quality of the nutrients in the soil. I don't know. It's just an idea.
We have some works in the agriculture field, and we don't use the UAV to go to the soil to take measurements. What we did in this case is to use sensors installed in the field, and also we use the UAV with a multi-spectral camera or similar. So we use the sensors attached in the field as ground truth, and then we calibrate the images that we capture with the multi-spectral camera. But we don't use these systems to well, I don't think the system is developed for this kind of task.
Okay, thank you. Yeah, for sure that is a breakthrough point in agriculture, because I think that a lot of application were developed in terms of, let's say, to assess the quality of crops and plants above the ground. But if we have to assess the quality of ground below the soil, this is the main barrier, especially in the width between 0 meters minus 1 to 2 meters. I think this layer is completely unknown sometimes, and for sure that this type of remote sensing techniques on board of drones can provide added value in agriculture. But I think that is a hot topic in the scientific community to be explored in the next years. So it's a good question. Okay, is there any more comment or questions? No. Okay, if this is not the case, we can move to the next speaker, the next panelist. So for me, it's a pleasure to have with us Dimitrios Skarlatos. He's Associate Professor in the Department of Civil Engineering and Geomatics in Cyprus University of Technology. Currently, Dimitrios serves as a visiting in Faculty of Engineering and Technology. His studies in rural surveying and PhD in photogrammetry, along with technical diving experience, allow him to be a lead surveyor in 3 archaeological shipwreck excavations of up to 45 meters depth since 2010. He was the coordinator of Imer Culture and 2020 Horizon project with 11 partners at a budget of 2.7 million euros, examining ways of raising public awareness for maritime cultural heritage, including virtual reality, beaches and underwater augmented reality tablets. So prior to his post in Cyprus, University of Cyprus, he was working 12 years as a freelance surveyor in Greece and has participated in different European projects along with several national ones. He is the academic representative of Cyprus in EuroSDR and co-chair of the International Society of Photogrammetry and Remote Sensing, the ISPRS, in the Commission 2, Working Group 9, about underwater photogrammetry since 2016. So the talk that Dimitrios is going to give is focus on the difficulties that today we can find to provide affordable subaquatic drones for 3D reconstruction applications other than oil and gas. At the same time, the talk is going to focus the potential for research and development in the field with clear and feasible targets. So the drones community leads the way and algorithms develop it so drones can be modified for underwater environment, which will create new markets for subaquatic drones in the near future. So it's a pleasure to have a talk focus on this topic because it's really, really novel. So please, Dimitrios, the floor is yours. Thanks a lot for staying with us.
Diego, thank you very much for the introduction and the invitation. So today I'm going to discuss about failures mainly, and this is for two reasons. First of all, I've been told that the audience will sympathize with you more if they listen about your failures and associate with you. And the second reason is that I had more failures in my life than success stories, so I have more material about them. So if you are here to learn about the key elements of using an ROV for underwater photogrammetry and developing one for such reasons, then you're in the right place. Coming from a similar background as Diego, so basically surveying, photogrammetry, and 3D reconstruction, I will give you the user aspect of using subaquatic drones for photogrammetry. And of course, at a certain point, I came in need of developing one of my own. The same thing happened approximately 10 years, a little bit more than 10 years ago, on developing a UAV for photogrammetry. Actually, I've been working on UAVs, aerial UAVs, since 1999 for documenting archaeological sites. So now, 20 years later, I've been asked to do that for underwater sites. Life is full of circles. So there have been several attempts on that aspect, on subaquatic drones. Here you can see two positions with towed bodies with a lot of sensors. On the left-hand side, you can see one designed for quite shallow waters. Of course, both of them are designed to map large areas and provide sea bottom mapping. On the right-hand side, you can see another one designed for deeper waters, and you can already see that there are several sensors on board, one looking ahead for navigation. Obviously, there is another one for the documentation itself. There are two video cameras and several lights. Both systems have some kind of control using flaps, and stabilization flaps. Now, if we go ahead, then we are talking about photogrammetric ROVs, remotely operated vehicles. You can see here one mapping the Antikythera shipwreck, located 55 meters below the sea surface. And Antikythera shipwreck was, it's not a concentrated shipwreck. Actually, the ship broke during the wreck formation process. So the content is sprayed along a very large area. And you can see here the ROV, it's not tethered, so it is controlled through acoustic modems. but it can perform very versatile and very sophisticated maneuvers to properly document the site. This was designed it has been used in at least, I know, 2 cases, one in Antikythera and another one in 30-meter depth. So probably it is designed for depths at least 100, 200, 300 meters. A second case is the ORUS 3D. This is a photogrammetric system developed by Beer Trapp specifically for, or at least aiming in oil and gas industry. It is a very expensive system. It is designed for working in total darkness. As you can see, there are 4 lights in total of 70,000 lumens. It can be adjusted in several ROVs. You can see here 2 implementations. It's been designed by Comex, and I've seen actually the prototype of it a few years ago in 2017. And as you can see, it has been used for archaeological site reconstruction. It has been used in Slendi in a site 110 meters deep for performing 3D reconstruction of the site, as well as in other shipwrecks, and you can see an airplane there. So this is a dedicated system. You can see it has 3 eyes. The central one is with a very high quality DLSR, and the other 2 are video cameras for SLAM, simultaneous location and mapping. And the other thing I would like to highlight is for you to note the proximity to the object. So you can see that the ROV needs to be very delicate and very precise in maneuvers in order to be, let's say, 1 or 1.5, maximum 2 meters from the object in order to attain high quality colored photos. Also, we have other kind of ROVs or completely autonomous underwater vehicles, such as this one. These are torpedo-shaped ROVs. Once again, they are particularly designed for photogrammetry. You can see that there is an array of lights to properly illuminate sea bottom. They are not tethered, so they can extend their range in a larger area, of course. They have a dedicated photogrammetric sensor and other sensors on board. Obviously, they need to be precisely located in the underwater environment in order to perform their task and take photos of the bottom. And of course, these are dedicated equipment. They are able to work both in deep and shallow waters, in demanding environments, and they are able to always produce excellent results. Either this is a complete 3D reconstruction of some oil and gas infrastructure in the sea bottom, so quite limited area, or provide seabed mapping for extended areas, and this is 2.5D mapping basically, but for very large areas and in preparation of some other oil and gas applications. On the other hand, we need to address the elephant of the room, which is the cost of such equipment. And in case you buy such equipment, you need to maintain it properly. You need to have a dedicated personnel to maintain and use it. In case you wish to rent it, then again, the cost is quite high. For example, I know for that ORUS 3D, they can rent, Comex can rent the ORUS 3D module for any ROV. You need to have vessel support. As you've seen, all this equipment and ROVs are deployed with cranes into the sea. And of course, such kind of expeditions have logistics and a lot of things that you need to organize beforehand. I will now discuss about my experience in the underwater environment and the way we are doing the 3D documentation and reconstruction of underwater sites, archaeological sites. And all this work has been done in collaboration with the Archaeological Research Unit of University of Cyprus and Professor Stella Demestica, who is the director of MARELAB and director of all these 3 sites. The first one, and the one I was introduced into technical diving for, it was the Masotos shipwreck. It's a classic Hellenistic period shipwreck located in 45 meters below sea level. I should point out that in such cases, in such old wrecks, you cannot find any wood because the wood is dissolved. At least the wood above the sand is dissolved throughout those years. And the only thing that you can see basically is the containers that ship had on board. In that case, amphoras. The ancient containers are amphoras. So the Masotos shipwreck was discovered 2007, and since then has been excavated many years. So the site is completely destroyed, as they say it in archaeology. Basically, there were approximately 500 amphoras exposed in an area of 17 by 8 meters. Of course, this area is much larger once you start excavating, because you get to find artifacts below the sand. And the problem there is the bottom time. So each diver has 20 minutes per day, basically, on the site. And then he has to follow a decompression sequence of 40 minutes or more. So let's say at least 1 hour of diving. In some case, I can prolong my stay there up to 25 minutes, but this means that I will have to extend my decompression sequence to almost an hour or plus an hour, just the decompression sequence, and I cannot dive the next day for obvious reasons. So the photogrammetric acquisition is at least tedious, and I give you already a hint about the importance of lights in the underwater environment. The next shipwreck I worked with was an Ottoman period shipwreck, Nisya site as we call it, in 28 meters. In that case, we had 2 excavation periods in 14 and 17. And being in a more favorable depth, you can have up to 2 dives per day with a long surface period of approximately 3 to 4 hours. Of course, the site will change within these 2 dives. So if we're talking about photogrammetric reconstruction, you cannot ask them to stop the excavation or doing any other things in the underwater environment. But still, we were able to have much better results because of the extended time, or the possibility to work longer times or more dives in the site. You can see here that both the excavation progress is much faster and the documentation is much more detailed in such cases. The last shipwreck that I work with is in Protaras. It's a Roman period shipwreck in 37-meter depth. So then again, we only have 20 minutes bottom time and a decompression of 30 minutes, and we may only dive once per day. Once again, this is a shipwreck in a flat sandy bottom, so 2.5D mapping. Obviously, we are doing 3D mapping, as you may see in the following slide. But then again, the time is quite limited to get the detail archaeologists actually need. So this is the result of 3 dives, 3 different divers using 3 different kind of cameras, some with lights, some without. And this is what is expected from the archaeologists. We didn't do any excavation on that side. We simply removed a couple of amphoras. So this was only done for documentation reasons and not excavation. Obviously, so far we've been approaching the reconstruction, the 3D reconstruction, using manned platforms, divers specifically. And we have several limitations. Time is the main limiting factor. So you don't have enough time to, 20 minutes is enough to completely describe and record a trench. So maybe an area of 3x4, 4x4 meters, but not enough certainly to document the whole site. And the other thing is that narcosis in 45 meters deep, or even 35, is strong enough, and you are not able, let's say, to set up your camera properly. So if you need to reset up the camera, probably you need to lose 2 or 3 minutes to reset it. So that's why we're not diving with other people's cameras, and we're diving with our own camera. And still, it's not easy to focus on other tasks in such depth. On the other hand, the main advantage of a diver who knows photogrammetry, and he is quite experienced in photogrammetric acquisition, is understanding of the site geometry, which is something you cannot easily have when looking through a monitor with 90 degrees field of view, for example. So using a diver has certain advantages. Then again, you may only use a diver of up to 60 meters. Xlendi actually in 110 meter depth is the only site that I know that uses divers for following the excavation. And you see on the left-hand side the process that we are using. The diver is going along a line, taking as many photos as he can. So no forward overlap. Forward overlap is not precise. And then again, he focused on the second line and is focusing on having a good overlap with the previous line. So this is what we are aiming at. This is a textbook, let's say, a photogrammetric acquisition on an underwater site, on Mazotos in particular, which much resembles what drones can do in aerial mapping, which brings us in the inevitable comparison of UAVs and ROVs. One comparison has to do with budget and cost. So you can see here, okay, the standard of aerial mapping, the DJI Phantom RTK, which costs approximately 5,000 euros. And you can see here down the blue ROV, which also costs 5,000 euros, but with limited, without a proper camera, for example. You only have the navigation camera, and you don't have any kind of positioning system, which is of high importance when you're trying to do mapping. Then again, you have the tether. You have a tether in most cases in underwater ROVs, which been used for back and forth communication, so to control the ROV as well as get the live feedback from the camera. In most cases in ROV, or at least in cheap ROVs, you have no navigation aid. You're working in a GPS denied environment, just like the previous presenters discussed. And you need something, you need some kind of navigation to ensure full coverage of the site before you leave. Also, you may use this kind of data to provide scale and orientation, as well as initial values for the forthcoming post-processing and battle adjustment. The visibility is another issue. So perhaps in a land site like Mazotos, so 25 by 10 meters, for example, you may use the drone flying in 10 meters height, have 2 millimeters resolution, and describe the whole site with 3, 4, 10 photos. This cannot be done in the underwater environment. You already seen that we need to be very close to the object and we need to acquire a lot of images. The other thing is power consumption. So usually we have, this is not a limitation in ROVs, especially if you're getting the power through the tether. But you have a long maintenance and cleaning time after each dive. And of course, legislation, there is no legislation that I know of at the current time about ROVs, while there is one, there's a European legislation about AUVs. Currently, there are many ROVs in the market, and actually the ones you see in the top bottom, left and right, they are quite cheap, they are below 2,000 euros. They are recreational, let's say, ROVs. And then you have more expensive solutions climbing up to 10,000 euros, just the basic version of those ROVs. For example, the Ocean Botics, it's about 8,000 to 9,000 euros. The trackers are 10,000, the boxfish is around 10,000. And then you can use the accessory list, let's put it this way, to add predefined cameras, predefined accessories onto your ROV. We had experience previously with ROVs. For example, University of Cyprus owned the Seabotics, the green one in the image. It was quite expensive. They own it since 2009, if I recollect correctly. It cost 30,000 euros. We broke the optical fiber tether twice with a cost of 5,000 euros for replacement. The service cost of any thruster or any maintenance service, it goes quite high, and we had to send the ROV back to the vendor. So it was very difficult, not to mention the video quality, which of course is the one you can see on the left. It was usable because we did manage to use it for 3D reconstruction. And actually this is a sequence that we use for 3D reconstruction on the left-hand side. But then again, it's far from optimal. And therefore we decided to, Cyprus University of Technology and my lab decided to invest in buying a blue ROV, 5,000 euros, and you get it in a IKEA-like box, so you have to assemble it yourself. But on the other hand, the flexibility and versatility of the platform is huge. The potential is huge, and actually has been developed as an experimentation platform. It's easy to use, to control using a game console, so everything is pretty cheap. It's been on board, it has a Raspberry Pi and a Pixhawk. So in case you flood, for example, if you have a leakage problem, probably you lose equipment of 1,000 euros. So it is cheap. We did face some difficulties in transportation, despite the fact that it is quite light and very small. And I'm going to discuss about them in a while. And of course, we proceed with initial trials in our little pool to understand the usability and of the ROV, and of course, try to calibrate the internal camera or external cameras in a little test field we made. And you can see here on the right-hand side the graphic user interface for the navigation, and you can see the added action camera on the bottom. The next phase, of course, were sea trials, either from a jetty here in Limassol or from a rocky beach nearby. And of course, the next trial was in Genovia shipwreck, modern shipwreck, where we found out that we had severe navigation issues. And this is mainly because of the ROV being unable to hold position. So in UAVs, in drones, you can leave the joystick and the drone will maintain its position, but it's not the same thing in ROVs. So if you have currents, the ROV will move, and you have very low visibility, so you are basically in the middle of nowhere, not knowing where you are going to. The same issues we faced it when we used it in Ischia, in 28 meters depth. We faced the same navigation issues, so you need the downline to follow, at least, in order to go down near the wreck and try to record it. But the most, the best application we had was in Protaras in 37-meter depth. We had faced some leaking issues with the ROV. Nevertheless, we have been able to follow the downline, not get tangled with other downlines, and there are a lot lines in the archaeological excavation site. And we were able to make a 3D of the site, and you can see we've used 2 action cameras underneath the ROV. They were positioned in looking slightly outwards, as you can see here. So to have a larger sweep width and cover more area in a single pass. The time interval was predefined in 2 seconds, set on board, and then release the ROV to the sea. And as you can see, the lights of the ROV are not enough to get any colors of the object. And inevitably, you come at a time that you understand that you need to build your own ROV with your own specifications, especially if you're discussing about such a small and affordable ROV. So what we need is a better camera, obviously. We need lights. We need some kind of navigation assistance in the underwater environment. We need more space to mount all this equipment and increase maneuverability. Remember, we need to be very close to the object, but we do not want to crash on the object. We need to reduce drag, especially if we are to send the ROV in depths that divers cannot follow, so 60, 70, 80, 100 meters, totally within the ROV range, and improve functionality and portability or handling, let's say, for us. This is the main diagram of the blue ROV 2. This is the part which stays on board, doesn't go down. And the rest of the equipment is down and closed into the body of the ROV. And there is no more space for anything else within the body. So you need to find a way to mount either a video camera or a DSLR or any kind of other camera, high quality camera, and you need them to communicate. So both in terms of controlling the camera as well as receiving the live view on the pitch hook and then transmitting on the Raspberry Pi and then transmitting that on the Surface laptop or laptops. So the camera requirements, we need a camera that can be controlled remotely, so you can change settings and you can have the live feedback from the camera. You need to be able to trigger, start, stop the video camera or start or trigger the camera through a cable, not Wi-Fi, not Bluetooth, because both of them are not working properly underwater. So you need a hardcore cable going to the Raspberry Pi and then will transmit that to the surface. Onboard storage, obviously, because the data are huge. Battery self-efficiency. And then again, we go down to traditional requirements of photogrammetry, so large sensor, quality optics, and affordable camera. The camera that we could use and fit it in our budget, it was a box camera. So it was a cinematography box camera which can be controlled with Ethernet cable. It's not of extremely high quality. It's not the best we can get. There are better cameras, box cameras, but with more, people with a larger budget. This is a micro four thirds camera. So you can select from a variety of lenses. It has 2.2 megapixels and a 4:3 aspect ratio. We had to design our own enclosure. So this was custom made. It was 3D printed initially, and then you can see the aluminum case here. We fitted the Ecolite dome in front, so proper underwater glass and rigs, and we have a very good camera with very small dimensions to reduce drag. The next thing you need to address is navigation assistance. And of course, Blue Robotics support this. They have developed a system, Waterlink they call it, with acoustic positioning sensor, basically a short SBL, short baseline acoustic positioning system, which is nevertheless not cheap. The cost is about 10,000 euros. I summed up the necessary equipment from the site last night. But on the other hand, you can navigate the Blue ROV. Okay, here is 3 times speed, but you navigate it and locate the point of interest. And in particular here, the point of interest is a small boat. So this can be done with, this is probably the best solution. The solution we decided to go for was to mount 360 sonar with a 50-meter radius, which can, as you can see, it will become much easier to follow the downline, and you can see what the video camera can see, the navigation camera. But on the other hand, the sonar can, on the sonar screen, you can clearly see the downline or any other underwater structure. So hopefully if you land within, let's say, 50 meters of the shipwreck, and then by moving around, actually you don't have to move around this 360 sonar, you can locate you can see where the shipwreck is and navigate yourself directly to the shipwreck. So this is an affordable solution which will provide some help, some assistance with the navigation. Other parts include a much thinner tether, so to reduce the drag, separate different connectors on the back of the ROV. So these are separable connectors, so we can separate the tether from the ROV, and we don't need to have a huge box with the tether and the ROV. And of course, payload skid to add more things, and the more thrusters on the exoskeleton to improve the maneuverability. All these things were bought from Blue Robotics directly. What we didn't buy from Blue Robotics are the video lights in total of 24,000 lumens. And this is the final implementation that we had. The upgrades cost approximately 20,000 euros. So we're talking about an ROV with total cost of 25,000 euros. We have 3 camera positions, vertical 45 degrees and forward. So we will be able to model even more complex shipwrecks than ancient shipwrecks. We have lights, and the navigation will be improved. And of course, the functionality will be improved. And on the other hand, we lost portability. So this is, it's not such a small ROV anymore. You can see the old ROV version enclosed in the red square. So now we have a much larger ROV, which will need some assemblance on the spot. It will require a large case, a medium case, and a reel. And the rib launch, the recreational inflatable boat launch, will be bearable an option anymore. So we'll need to find some way of a support vessel. So not everything is good. So closing now, we're still far away from having a perfect solution. We need to develop in-house complementary software for visual odometry and real-time photomosaicing, which will be useful for the sites that we're working with. So 2.5D objects. We need to find a way to do coverage checking before we leave. And we need to combine the poor navigation data from the pitchhawk to somehow provide scale orientation on the final 3D reconstruction. On that part, I think that the community will learn from the UAV community, where there is the possibility of simultaneous location and mapping. Skydio has included already in their drones. So you can define the area of interest and the drone will create a 3D model, coarse 3D model of the site, and then decide on the approach and will approach and come closer to the object until incrementally, iteratively, until it reaches the quality, the resolution that you have defined. So I hope that this will be ported at some point in the ROVs. We are roughly 10 to 15 years behind in ROVs, but at the very end, this will be ported in ROVs as well. So this is a fascinating and challenging domain in the underwater environment. There are a lot of opportunities. I know drones have not completed their full potential in air, but we are lagging behind in ROVs. So there are several possibilities. In the middle of difficulties lies opportunity for young researchers to join us. For those of us who wish to join us, please consider registering in ISPRS Working Group 2.9, the Underwater Data Acquisition and Processing, to get more updates about ROVs. So thank you very much once again.
Thanks a lot, Dimitrios. It was incredible, the presentation, and very, very exotic, the application of drones in underwater environments. So for me, it's great. And as you was saying, it's an unexplored, let's say, territory. So there are a lot of gaps and a lot of ways to be incorporated in this subaquatic domain. So yeah, it is great. The first question from my side, before giving the floor to other participants to ask you questions, we are collaborating with the Army in a project related with drones in aquatic space. So they were considering to acquire a subaquatic drone, but in the end they acquired an aquatic drone. I mean, they only acquire data from the water, you know, navigating the drone. So they put on board different sensors, sonar, and so on. And according to the first results, I think that it was very good. The system that they acquired is a really powerful ship. It is not very big, but the sensor that they put on board allow them to assess the coast, the different things that they want to control. I was wondering if you consider that your technologies, your drones combine both possibility, the possibility to acquire data from, let's say, subaquatic domain and also from the top.
Yes, you're talking about unmanned surface vehicles, I suppose, right? The question is, yes, there is. This is an even more trendy area because they are cheaper to acquire. You don't have to mess up with the underwater environment and increased depth, which increases the problems. So you only need to make the equipment IP68 perhaps. So this is much easier. And on the other hand, you can attach more payload to them. So you can attach, of course, you can use the GPS, GNSS sensor on board. So you have perfectly the position of the vehicle. And then again, you can attach several other heavy-duty sensors like side scan sonars or multi-beams or whatever. And you get a lot of information. Actually, you can even, for clear water, you can, with clear visibility, you can even use vision, so traditional cameras, to get a very good orthophoto model and 3D model of the bottom. So yes, there are a lot of people working on it. You can buy a surface vehicle for approximately 20,000 euros and then add on the equipment that you wish on, ready-made with GNSS support, everything, and you can add on your equipment there. So speaking of drones, unmanned surface vehicles are a very good option, but I think that we need to meet the legislation about the surface vehicles soon. Because if they populate, the coastal sites, we will have a trouble.
Okay, thank you. Considering the sensor that you put on board, it is clear that you focus on passive sensor based on photogrammetry. So I was wondering about the active sensor. Did you consider to put on board some active sensor?
The active sensors that I'm aware of, and I'm talking about LiDAR sensors basically, they are pretty expensive still.
Okay.
And they are pretty heavy. So before considering doing it, you certainly need to upgrade in the ROV. It needs to be much bigger. So industry level ROV, not game console level ROV. And then again, you need to be able to afford 10,000 euro, 100,000 euros for the laser, which is heavy. The implementations I have seen so far are tripod based. So you need to put a tripod, have the scan of the area. Visibility also is an issue. So you have to, it's around 3 to 4 meters max. You still don't have color information. So who is going to operate that? Who is going to put it there? So do you need divers? Do you need saturation divers to use that? So far, I've seen that the ORS 3D and photogrammetric approaches work better in the underwater environment. You have plenty of time to work yourself around the object, take the photos you need, and make a very good photogrammetric font.
Good. Totally agree. Maybe if the audience is not aware about the, let's say, the complex environment that you have to face in subaquatic terms when you have to, let's say, adapt the photogrammetry and the computer vision to solve the equations. When you are working in photogrammetry in underwater environment, you have to, let's say, to reconfigure, readapt some equations to solve the pass from 2D to 3D. So can you explain very briefly to the audience, maybe to the people that are not expert in photogrammetry, that we need also to adapt the equation and we need to adapt photogrammetry to deal with this complex environment?
Yes, the problem is that the main photogrammetric equations depend on the fact that the light rays propagate in a straight line, which is more or less true in air. But in the underwater environment, you have the light ray passing from water through glass, thick glass, actually, and then through air, and then come to the camera. So you need to adjust your approach in order to take that into account, and most softwares cannot do that. The commercial softwares cannot do that. So you need to solve it with in-house software, let's put it this way. The lucky thing, the good thing is that when you're using a dome port, not a flat port, but a dome port, and you position the camera correctly in the center of that dome, then the problem of water refractions basically comes down to self-calibration of the camera. So since you're anyway using self-calibration, if you don't have a flat port, then you can easily use commercial software and self-calibration to solve the problem. This is not true if, for example, the camera is not positioned within the center of the dome, okay? And this is also not true if the camera is by any means moving within the dome, okay? So most navigation cameras, they have the ability to move inside the dome. So then you cannot assume that the self-calibration will solve the problem because at each point you have a different camera based.
Thank you. Thank you for the didactical clarification for the audience. So it's time for questions. Is there any questions in the chat? The people is saying congratulations, Dimitrios, for the work done and for the presentation. So I think that it lived up all the expectation this last talk. So thanks again. So is there any questions? I think that in the chat there is no more questions. So Elena is saying that the certificates of attendance to this webinar are going to be available in the webinar attendance on their SA Forum profile. And to access to this certificate, you have to access to the Visit Sites Forum.net account and create an account if you didn't do it before. And then simply you can log in with your account and get the certificate in the My Certificates section, okay? Is there any more comments or question for Dimitrios? Okay, this is not the case. Maybe it's a bit later because we are extending more than 2 hours now, 14 minutes. So thanks again, Dimitrios, for the presentation, for your expertise and your knowledge. It was a pleasure, and extend all the thank you also for the previous presenters, the previous panelists, to Luis Miguel and Antidio for their brilliant presentations. The first focus on all the capabilities with the research center of CATEC, with the robotics arms, with the possibilities open with SLAM technologies and different application for surveillance and so on. The second presentation focused on, let's say, the assessment of the health of bridge with different prototypes, different verticalization of the control of these structures with very, very interesting approach. And finally, Dimitrios with these insights in a subaquatic domain, open the new possibilities of drones and photogrammetry. So thanks again, and it was a pleasure. So Elena, the floor is yours.
So yes, just a quick thank you to you as well, Diego and Pablo, for chairing the webinar. You have been amazing chairs, and also to the speakers that two already left, but thank you, Dimitrios, for your presentation. You, Diego, already said about the certificates. There's information there in the chat. You can also subscribe to the newsletter, so you would be receiving more announcements of future drones events, because this is the first one, and we are thinking about doing more. And I think that's all for now. Also a reminder that the webinar recording will be posted at the webinar's webpage. And I hope you all enjoyed. I wish you good morning, good evening, good afternoon, wherever you are in the world, and hope to see you soon in future events. So thank you very much, and bye-bye. Bye to everyone.
Thank you, bye.
Thank you, bye.